Hi, welcome to my talk on summary index idempotency. My name is Kaye. I'm also known as IT Whisperer in the Splunk community and on Slack. I'm employed by the British telecoms giant BT. I started using Splunk in August 2018. 2 years later, in 2020, I joined the Splunk community, and I was inducted into the Splunk Community Trust in 2021. You can find me at IT Whisperer. My strapline for this virtual conference says I am the only person in the room who knows what idempotency means. Hopefully, by the end of this talk, there will be a few more who understand it and how it can be applied to help make a more robust summary indexing process. The agenda for today is going to be a description of the problem. What is the issue I am trying to solve? A view of the dataset I'll be using and how I've created it. The dashboard used to visualize the example. The data sources configured for the dashboard. How we can use summary indexes to improve the performance of the dashboard. One of the potential problems with summary indexes, and what idempotency is and how it helps. A little on SUBSEARCHES and some of the issues, and finish off with some caveats and other possible use cases. So the first thing is a statement of the problem. When a summary index needs updating, how do we update the summary index without double counting? A summary index is often used to maintain aggregated statistics like counts and sums, and it is this use case that we are going to consider. These statistics are often grouped by time periods, for example, days, which is the example I'm going to use in this talk, but you can use other dimensions to group the statistics. Sometimes there are occasions when these statistics need updating. For example, there may have been some late events that we missed first time around, and we now need to include them in our aggregations. However, what we want to be able to do is to make sure that the summary index is only updated with these missed events. That is, only update the summary index with the new data rather than also double counting the previously aggregated data. But how did we miss these events in the first place? Here is a scenario based on a real-world example to demonstrate how data can be missed. Consider a couple of transactions. Transaction A starts at 1 minute past and lasts 3 minutes. Transaction B starts at 3 minutes past and also lasts 3 minutes. The access log for transaction A is written at around 4 minutes past when the transaction ends, so that it can include the duration and the response status. However, the timestamp at the beginning of the access log record is often the start time of the transaction. For example, Apache HTTP server is often set up to log access to service URLs in this way. I've also seen it in load balancer access logs. It will often be this timestamp that is used when we index the event in Splunk, especially given that this is the first timestamp in the record and it is easy for Splunk to recognize. Transaction B access record is written to the access log at around 6 minutes past when transaction B ends. The access log is ingested into Splunk and indexed. When the access log record for transaction A gets indexed, it is given a timestamp in the time field of 1 minute past. Of course, there's a lag between when the event is written to the log and the time it is indexed with. This is a real lag, if you like. However, because the timestamp used for the event represents the time when the transaction started and is only written to the log when the response is known, this introduces an artificial lag, if you like, comparable to the duration of the transaction. And when the access log record for transaction B gets indexed, it is given a timestamp in the times field of 3 minutes past. Let's assume we want to count transactions in 5-minute periods and store this aggregation in the summary index. If we count the transactions at 5 minutes past, or even 5.5 minutes past, only the access log record for transaction A would be in the index for that time period, and therefore included in the aggregation. And when we count the previous 5 minutes at 10 minutes past, or even 10.5 minutes past, we would miss the access log record for transaction B, since it is indexed for the first 5 minutes. We could, of course, count the previous 10 minutes every 10 minutes, but then the summary index is up to 10 minutes behind the indexer, and there could still be transactions which span the gap and would be missed. Or we could count the previous 10 minutes every 5 minutes, but then we would be double counting most of the events. Other scenarios exist whereby events are missed. That is, they are in the raw index eventually, but have not been included in the summary index aggregations. The dataset I'm going to use to demonstrate the summary index idempotency is based on the Splunk tutorial set. So if you want to follow along or work through the example later, you can pick this up from the Splunk website. I just downloaded the tutorial data files. Specifically, I'm going to be using the vendor sales source type data. To make it a bit more interesting, I have multiplied this data set by 10. I'll show you how I did that in a moment. Also, to make this a bit more interesting, I will create an extra field which I've called region, which I calculate as being the vendor ID divided by 100. This gives me another dimension by which to group the data. I also created an extra overlapping data set to represent late data that might be coming in for this scenario. So how do we create the additional data? What I did was look at the vendor sales source type data. I created an extra field called increment and added that to the vendor ID, the account ID, and the time. I also cycled the code through to the next code in the sequence. I recreated the raw field using these new values and exported it to a file. Note that I found in my environment the file works better in Unix text file format rather than Windows. I did this 9 times with a different increment, 1 through 9 each time, and loaded this data into the same index. I also created the late data set with an increment of 100, using 1/10 of the original data, so that the vendor IDs are bumped into the next region. Next, I created a dashboard covering the time period that the vendor sales data was for. The dataset is generated when you download the files and has a time span of 7 days prior to the time you downloaded your copy. But take a note of the time period you got and set the time period for the dashboard searches accordingly. This dashboard is counting the events by day and region. I will show you how the data source for the chart is configured in a moment. First, a quick look at the data behind the chart. Note the value for region 12 on the 27th, 7,984, as we will come back to that later. Looking at the data source configured for the chart, there is a parent search which reads the raw Buttercup Games index. Buckets the time into daily bins, creates the region by dividing the vendor ID by 100. Note the use of the floor function to keep this as an integer. Then it creates the first level aggregation statistics, counting the events by time, vendor ID, region, and code. These being the dimensions I might want to slice the data by. I tend to use multiple dimensions so that the same parent search can be used for different charts and tables in the dashboard. Next, there is a change search, which creates the actual data for this particular chart, which sums the counts by region. The important thing to note here is that every time the dashboard is loaded or refreshed, the raw Buttercup Games index is searched. Depending on the size of the data set, this can be quite time and resource consuming. So in order to optimize this, we look at what summary indexes can do for us. First, we need to create a summary index. You generally need to be administrator or power user to create indexes, or ask your administrator to do this for you. Then we can populate it with aggregated data. Using the same search we used for the parent search before, we generate the first level aggregated statistics from the raw data in the Buttercup Games index. We add these statistics events to the summary index with the collect command. Again, you may need administrator or power user rights to do this. We give the collect command the summary index that we want to update, Buttercup Games _summary, and the name of the search. For this, I've chosen vendor sales. If you choose a scheduled report to update the summary index, the name would normally default to the report name. We also want to preserve the timestamp with the add time equals true option so that we can match the events later. Once we've got the data in the summary index, we can update the search for the dashboard parent data source to use the summary index, Buttercup Games _summary, rather than the raw Buttercup Games index. We need to use the search name parameter with the matching name from the collect command, vendor sales in this instance. We also have to make sure we specify the fields we are interested in from the summary index. By doing it this way, we do not have to update the search for the chained data source. Okay, that's the dashboard sorted out, but what about the summary index? If the report to populate the summary index is used multiple times for the same time period, duplicate entries would be created. This is where idempotency comes to the rescue. Idempotency is the concept whereby an action can be repeated with the same inputs and the result is the same as the first time the action took place. Consider a read operation. By definition, it doesn't change the data, so is inherently idempotent. But what about create, update, and delete? If we create an entry in a database, for example, with an operation, if the operation is repeated with the same inputs, unless the operation is carefully written, we may end up with multiple objects created. If we update an object, such as incrementing an attribute, if the operation is repeated or replayed, we could increment the attribute too many times. Delete is slightly different. Once something is deleted, it is usually assumed to have been deleted. But a delete operation will often return an error if it can't find the object to delete. Coming back to our issue, since the report is counting events across a number of dimensions, so long as the base data does not change, we want the counts to be the same. This means that if we count the events and then subtract the corresponding count values already stored in the summary index, we should end up with a net sum of 0. To apply this in our case, we update the summary index report search so that the existing entries from the summary index are discounted. We do this by appending the events from the summary index for the same time period, but we negate the count values. We then add them to the counts we've just calculated from the raw index for the time period in question. Assuming nothing has changed in the raw index since the counts were entered into the summary index, the total sums will end up 0. So we only really want to add anything where the net sums are greater than 0. Now we can run this report multiple times, accidentally or deliberately, and the counts will remain unchanged unless the raw data changes. So let's see that in action. When we run the report a second time, when there are already entries in the summary index, instead of getting 0 results, there are some events returned, which means some of the raw events have not been discounted. If we had continued to add these events to the summary index with the collect command, or because a report is configured to update the summary index, we would effectively be double counting some of the data. So why didn't it work as we would have liked? As we know, sub-searches are limited to 50,000 events. We can see this in the job status. If you run this supposedly idempotent update with a large time period, there is potential for the sub-search to be truncated, thereby setting up some double counting. With the data I've chosen to use, where we have got 10 times the original vendor sales, if it was left as it was, it would not work because the sub-search would get truncated. This means that some of the statistics would not get discounted, and we would end up with positive counts, effectively double counting some of the events. Although there is a message in the job inspector, the collect command would still be executed, updating the summary index. There are a couple of things we can do here. Firstly, we can try to detect when the truncation of the sub-search has happened. and only continue if the subsearch has fewer than 50,000 events. Now, this modified report can update the summary index without double counting the existing values. Although if a subset has 50,000 events or more, the summary index would not get updated with any new data from the raw index search. Bear in mind that you should keep an eye on it or set up an alert and make sure the subsearches are not exceeding 50,000 events and therefore not updating the summary index. Another thing we could do is to fragment the subsearch such that the fragments have fewer than 50,000 events. Fortunately, in this instance, the way I've set the data up, there are fewer than 50,000 statistics events per day. Therefore, I can fragment the subsearch into daily chunks so that each chunk contains fewer than 50,000 events. Now, there are a couple of ways of doing this. One is to use the where command and set up some bounds for the time field so that each chunk picks out one day at a time. The other way is to extend the subsearch to have different values for earliest and latest, essentially doing the same thing as we were with the where command. In my environment, in the tests I have done, this second way was actually quicker because the events from the subsearch were filtered as early as possible. In fact, it was almost twice as fast, although you should verify this in your own environment. So the basic idea is that you set up a number of appends, depending on how many days or time period fragments you want to cover in your report that you're adding to the summary index. And for each day, you append the summary index search for that period. The same negation of the counts happens for each time period, and you end up doing multiple appends. This avoids the 50,000 events limitation. Now, by using fragmentation, this new report can be used over larger time periods to update the summary index without double counting the existing values. As you could see, the report returned no results. Therefore, the collect command would have nothing to update the summary index with. We can see that all the events were processed. And from the job status, there were no truncated subsearches. The late data created earlier used an increment of 100 to push the vendor ID to the next region. Adding this data to the raw index and rerunning the idempotent summary index report to update the summary index. The chart now looks like this. There's not a lot of difference in some of the columns, but significantly, the values haven't doubled. And there is an additional series for region 51. This is now the data behind the chart. Note the value for region 12 on the 27th again. Now it is 8,081. If you remember, it was 7,984. In conclusion, this technique works well for counted or summed aggregates. For other aggregates, perhaps not quite so well. Things like mins and max could work simply by renaming the min or max from the summary index and comparing it with the corresponding min or max from the raw search. and keeping the event if they're different. Similarly, for mean averages and standard deviations, etc. Although potentially you might want to round figures before comparing to diminish the impact of floating point calculation variations. The key is obviously restricting the subsearches to 50,000 events. This does not have to be based on time, although that is probably the easiest dimension to use. Any of the dimensions from the first level aggregate search, for example, region, might have worked, although actually not in this instance, as some of the regions are overrepresented, or perhaps a combination of region and time might have worked. There might be another way of breaking up the subsearch into non-truncated chunks. You just need to find the right approach for your use case. Late data is a term I have used to indicate that the raw index has additional events which were not in the initial search when the summary index events were first added. These additional events can appear for a variety of reasons. For example, it could be network lag, or additional data sources coming online, or like in the real world transaction log example I used earlier, that kind of thing. There are probably many other use cases where this might be useful. In summary, we have looked at how summary indexes are used to aggregate statistics and how they might get misaligned with raw data. We looked at how the tutorial dataset can be used to demonstrate the issue. We looked at how to modify a dashboard parent search to use summary indexes in place of a raw index. We looked at some of the issues with summary indexes in dealing with late data, and how idempotency can be used to bypass some of the issues by using subsearches, and how to fragment subsearches to make a more robust process. And that's it. Thank you for your time.